Kia ora, it's Mrs. Goodson, and this is the second video for Chemistry 3.4. The learning intention for this video is to teach you how to write the electron configuration for the first 36 elements with SPD notation. In this video, we're going to look at some example questions, some exceptions to the rule, which is chromium and copper, and the electron configuration of ions. Just a reminder, ions are atoms that have lost or gained electrons to become charged particles. For example, sodium, chloride, and iron 2+. So, for example, we're going to look at these elements and we're going to write the SPD notation for them. Remember that you'll be given a copy of the periodic table of elements in your exam. So I've put one up here for us to look at. First of all, carbon. So you find carbon on the periodic table. It's got an atomic number of 6 over here. So it's going to have 6 protons and 6 electrons. So the first shell will be filled. So 1s2, 2s2, 2p2. So the first shell is the first row, and then the second row is 2s2, 2p2. We'll count these numbers. 2, 4, 6. It's got 6 electrons. So the next example is phosphorus. Get rid of this carbon. Phosphorus. Phosphorus is got an atomic number of 15. So we need 15 electrons. The first one is 1s2, 2s2, 2p6. 3s2, so we're up to the third shell now, the third row here. So we've got 3s2 and then 1, 2, 3 in the p block. So we've got 1s2, 2s2, 2p6, 3s2, 3p3 with a total of 15 electrons. The next example is chlorine atom. Okay, so the atom means it hasn't lost or gained any electrons. So chlorine atom is number 17. It's got an atomic number of 17. So it's going to have 17 electrons. So we can use a periodic table. So 1s2, 2s2, 2p6, 3s2, and then up 1, 2, 3, 4, 5. So it's going to be 3p5 for a total of 17 electrons. Gallium, that'll be a new one to you, I think. So number 31 over here. So it's going to carry on from the same as chlorine. So it's got a full shell up to 3p6. We're going to fill in 4s2. So this is the same. That's why I've underlined that part there. Then 4s2 here. And then we go on to the D block. So gallium's got a full D orbital. So we've got 3d10 and then just 1 and the 1 electron in 4p1. Okay, so that is the electron configuration for gallium. Now we can, up to argon, it's going to be the same. So up to here, this part here is argon. So past gallium, it's always going to be the same. Or past argon. So we can write argon, that was our noble gas there, and then just write the bit on the end. That's an acceptable way to write, a slightly shorter way of writing the electron configuration. Now let's have a look at iron. Iron metal is a transition metal. So let's find it on the periodic table. Where's that pen? So we've got iron here. Atomic number of 26. So it's going to have 26 electrons. So up to argon is the same. So this part here is the same as for argon. And then we've got 4s2 and then 3d6. So 4s2 is here. And then 1, 2, 3, 4, 5, 6. Okay, so the d orbital has 6 electrons. Now there's a couple of exceptions to this, the way that you fill the orbitals. The exceptions are chromium. So chromium is atomic number 24. So it does have to have 24 electrons. It's chromium here. And so argon is up to argon, it's 18, that's fine. But because it's got, it's here, you would think maybe you do 3d4. But because it gets stability from having a half-filled d shell, we actually half-fill the d orbital, so 3d5, and you only need one extra electron for 4s1. The other exception is copper. Copper is atomic number 29, and it also gets some stability from having a full 3d orbital. So these two are an exception because they gain stability by promoting an electron from 4s to 3d. And these half-filled D shell in chromium and the full-filled 3D shell in copper makes it a more stable option. So you need to remember only for chromium and copper elements, you only need to put one electron in 4s1 and half-fill or full-fill the D shell. Okay, so ions. So ions are atoms that have lost or gained electrons. So the first thing you need to do is calculate the number of electrons present in monatomic ions. So it's the number of electrons is going to be the atomic number, the same as elements, but minus the charge of the ion. So I'm going to do a couple of examples for you here. Potassium ion and fluoride ion. So potassium atom has 19 electrons, but potassium ion has lost an electron because metal ions lose electrons, so it's only got 18 electrons. Let's have a look at a non-metal. So fluorine atom has 9 electrons and fluorine ion has 10 electrons because it's gained 1 electron to get a full shell. So ions and atoms with the same electron configuration are known as isoelectronic. So let's look at some examples. Use the same rules as with atoms. Just remember that the ion will either have more or less electrons depending if the ion gained or lost electrons. So cations, metal ions are positive and they have lost electrons, and anions, non-metal ions, have gained electrons. So let's look at oxide, which is O2 minus. So it's the oxygen atom. The oxygen atom is 8, and then it's gained 2. So 8 minus 2 is adding 2, so we've got 10 electrons. So the oxygen atom, just to compare, has got 1s2, 2s2, 2p4, total of 8 electrons, compared with the oxygen or the oxide ion, 1s2, 2s2, 2p6. So it has gained 2 electrons here, so it's gone from 4 to 6. And now it's got 10, 2, 4, 6. It's got 10 electrons, or it's got it's isoelectronic with neon. So let's look at some examples. So fluorine atom is 9, and it's got a -1, so it's got 10 electrons. So it's 1s2, 2s2, 2p6, so 2, 4, 10. So it's got 10 electrons. Sodium atom is here on the periodic table. It's got 11, but it has as a metal, it has lost 1 electron, so it's got a charge of +1. So it's 1s2, 2s2, 2p6. It is actually the same, right? So it's got a full shell. It's isoelectronic with fluoride ion. So 1s2, 2s2, 2p6. Chlorine is over here, and when it forms an ion, it gains 1 electron, which is shown by the charge. So it's going to have 18. So it's 1s2, 2s2, 2p6, 3s2, 3p6. You just check by adding up all those numbers, and it adds up to 18. Calcium is here, is 20, and it has lost 2 electrons. It's a metal ion, so it's got a charge of 2+, so it has 18. So it's also the same. Remember, we can draw that as argon. Okay, so it's isoelectronic. Bromine is 35. It is a halogen, so it's going to gain 1 electron. So we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. So it has got a full shell, and it can be written in the short way because it is the same as isoelectronic with kryptonite. Okay, transition metals are in the D block. Metals between atomic numbers 21, which is scandium, to 30, which is zinc. They have valence electrons in both the 3d and 4s orbitals. Those ones are all called valence electrons. They do not necessarily lose all their valence electrons when forming positive ions. They will always lose electrons in 4s2 before any of the electrons in the 3d orbital. This is because 4s is further away from the nucleus. So let me show you with some examples. So vanadium, we're going to look at the atom first. Vanadium is atomic number 23 over here on the periodic table. And so it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. We'll fill in the 4s first. So 4s is here. Fill that in first, and then 1, 2, 3. So vanadium is 3d3. But when it becomes an ion, it's going to lose the 4s2 electrons first. So it keeps these, but it loses those, and so that is the electron configuration for vanadium 2+. Now we did iron earlier. Iron is up here. It has got 26 valence electrons. So it's 3d6 at the end. Fill in the 4s2 first, but when it loses electrons, it loses the 4s2 ones first. So iron actually forms two ions. It's got iron 2+ and iron 3+. You might remember that. So the first one is we've got rid of the 2 electrons. It's lost 2 electrons, so it's got a charge of 2+, and so we've left that out. 4s2 is gone. If we need to lose another electron, we just simply take it from the d orbital. It's another valence electron, and it's 3d5. Okay, so those are the iron electron configurations for iron 2+ and iron 3+, the two oxidation states of iron. And so we've reached the end of the video, and thank you for your time.